Okay, so our next speaker is Shadi Dayeh, here locally here at UC San Diego, and he'll be telling us about his high-density microelectrode arrays, right? And what it tells us about how the brain works. So, Shadi.
All right. Well, thank you very much for the introduction and for including me in this great symposium. My lab at UCSD leverages advanced semiconductor device processing in order to develop and deploy neurotechnologies that with an attempt basically to bridge the gap between high resolution and large scale coverage to be able to understand how the small potential fluctuations on the individual cellular level coordinate large scale function over extended regions of the brain. Now, to do that, we use a number of devices, including intracellular nanowire arrays in a fishbone architecture that have potential to measure intracellular recordings from extended neuronal networks in intact brains. We also work on penetrating microelectrode arrays with a flexible backing that are also scalable to thousands of channels. And we also work on ECOG devices with larger scale coverage. And all of these devices are human compatible. So perhaps this device is the minimally destructive or least invasive device that we use on the lab. And we will be focusing today on recordings done with these ECOG devices. Now, in the last 2 years, we've seen a number of developments in the field where recordings with thousands of channels has been demonstrated in rodent animals. There is a remarkable work came out from Lauren Frank's lab at UCSF, where they demonstrated recordings with polymer electrodes that were placed on silicon-hardened shanks and recorded over extended durations of time. And more recently, the work that came out from Neuralink. But for clinically viable devices, the most impressive advances came out from Eddie Chang's lab at UCSF, where he uses epilepsy-type grids, such as those that are shown over here, to record neural activity and use decoders for this recorded activity correlated with the kinematics of the mouth movements in order to decode speech. Now, there are other labs working on this, including Nathan Krohn's lab at Johns Hopkins. Now, the most advanced clinical electrode contains about 256 channels. This is an EdTech electrode, 16 by 16 channels, with 4 millimeter spacing, a diameter of about 1 millimeter, and this is extending over a large cortical area of 6.4 centimeters by 6.4 centimeters. But this clearly undersample neuronal function, so if you want to include higher channel count, we would want to reduce the diameter and bring these electrodes closer together. And when we do that, the impedances of these electrodes increase, and therefore the recording quality is compromised. What we're doing at UCSD is using highly electrochemically sensitive electrode materials that I will talk about today on very thin substrates. So these are 10 micrometer thick. And they'd allow us to record in a 1024 capability over an area of 3.2 centimeters by 3.2 centimeters when we have a 1 millimeter spacing between the contacts. Diameters are variable, could be 20 microns. Conveniently, we use 50 to 100 micron usually. And this has a long extender so that we have clear coverage between the electrode being placed on the cortical surface and the recording electronics that has to be cleared out from the surgical field. Now, being thin is very important because we want these electrodes to be compliant to the brain movement and to maintain the conformality on the surface of the cortex so that we have excellent coupling of neural activity to these electrodes. So today I'll start by talking about why do we need low contact impedance electrodes and how do we make them. I'll focus on a new electrode material that's developed in our lab, the platinum nanorods, and describe its electrochemical properties. And then I'll show results about their use during intraoperative monitoring across multiple clinical centers in epilepsy monitoring, some language tasks, and more recently in motor mapping. So like in any engineering problem, we all know that surfaces and interfaces actually determine how the system performs. And most conventionally, the electrode material that's has been used in neural interfaces include P.PSS. We've heard the previous speaker, Ricky, talk about electroplating P.PSS on the electrode to lower the electrode impedance. And this is a one-dimensional polymer that has gaps in between the polymer chains, and that allows ions to intercalate into the polymer material and participate in the charge transfer. So it gives it the characteristic of volume sensing as opposed to surface sensing. Rough electrodes has been also used, including sputtered iridium oxide films, and those typically give low impedances. Impedance depends on diameter, and we'll describe that in a couple of slides. Now, but what really determines how good a material can be for electrochemical sensing could be inferred from this volcano plot that electrochemists use. This is looking at the exchange current, which is the equilibrium, zero potential current across the electrode material in solution as a function of the bond length. If we have a small bond length between the ion and the surface of the electrode, that means the residence time of the ion on the surface of the electrode is short. So you don't have enough time to participate in a charge transfer, and the currents are usually small. If we have a large bond length, that means the residence time is long, so we can have one charge transfer, but we block the site so that no additional ions come and participate in this charge exchange. So we need just the right amount of energy for ions to come sit on the electrode, participate in a charge exchange, and then clear the way for other ions to come and be sensed. And that's why platinum is one of the best catalytic materials that we use in catalysis, electrochemical catalysis. Now, if we want to look further at why impedance really matters for recording, this can be inferred from the plot that we see right here. This is using planar platinum electrodes. We're looking at the noise voltage as a function of frequency. And for different diameters, we go from 1 millimeter to 20 microns. We notice that the 1/f noise increases by a factor of about d squared as we reduce the diameter of the electrode. If we use a low impedance material such as P. or platinum nanorod, even though we go across these multiple scales, the 1/f noise is constant because we have a lot of adsorption sites, so the random motion of ions in the vicinity of the contact does not induce a lot of noise. Now, an additional consideration for the thin electrodes that we use is that there is a thin insulation layer between the metal leads on the electrode and the surface of the brain, about 2 microns usually to 10 microns. And therefore, we have a large parasitic capacitance between these metal leads and the surface of the brain. And this large parasitic capacitance can short the input of the amplifier. So if we have a high impedance electrode and a low input impedance to the amplifier, most of the voltage drop that we're seeing at the contact will be dropped across the electrode itself. So in order to mitigate this effect, we need to really reduce the electrode impedance and to preserve the strength of the neural signal that we're recording. So how do we make these one-dimensional platinum nanorods on flexible substrates? Usually to make one-dimensional structures, we need to use high-temperature processes, but flexible substrates have a low thermal budget, maximum about 170 degrees C in the case of parylene, case of polyimides about 300 degrees C. So we use something called selective dealloying or a selective dissolution of materials. We could deposit two materials together, silver and platinum, and we put it in a solution which can selectively etch silver versus platinum. And as this process continues, for surface energy minimization, silver comes out of the alloy to the surface and gets etched by the nitric acid in this case. Now, most conveniently, we get this nanoporous structure, but if we tune the deposition conditions, we could get the remaining platinum structures to be in the form of cylindrical rods. So this is what we are referring as platinum nanorods. They're 400 nanometer tall and about 50 to 100 nanometer in their diameter. Now, if you look at a slightly larger field of view image of what a single microelectrode contact looks like, this is shown here. It's a 50 micron diameter contact. And you can see that there is a recession inside the contact. So if we take a line cut and we look in the cross-section of the contact, we see that the rods are actually at the bottom of a mesa. And this mesa is formed by paraline. So what touches the cortical surface is actually the surface of the paraline, and there will be no shear forces on the rods to break them out. So this is important for their mechanical stability. Now, if you look a little bit closer in the transmission electron microscope, we see that these devices are built on paraline with a thin adhesion layer, a platinum base, and the rods themselves are porous so that you have a slightly larger surface area to volume ratio. And if we look even closer, we see that there are a lot of these sharp facets, and these facets induce charged dipoles that usually lower the work function and enhance the electrochemical activity. So it's not only a gain in the surface area, but it's also a gain in the electrochemical interaction itself. Now, if we look at the impedance at two different frequencies here, 10 hertz, 1 kilohertz as a function of diameter. For platinum, which is yellow, it's the highest impedance. Platinum nanorod is the green, which is the lowest impedance for all diameters. And then P dot PSS is comparable in its impedance to that of platinum. Now, and the values for different diameters are shown over here. At 1 kilohertz, you get about 20 kilo ohms for 24 kilo ohms for a 40 micron diameter contact. And that's for P dot. For platinum nanorod, it's about 25 kilo ohms. And for planar platinum, it's about 200 kilo ohms. So about an order of magnitude or so lower than planar platinum contacts. Now, this is important also for stimulation. If we inject the same charge across both electrodes, platinum nanorod and platinum, we can see that we build a smaller transient voltage across the platinum nanorod compared to that of platinum. Therefore, it's safer to inject charges with these low impedance electrodes compared to the planar metal electrodes, because we would have more room to inject more charges before we reach the water hydrolysis window. Right? And this is quantified with the charge injection capacity, the amount of safe charge that we can inject per unit area. And it's about 16 times higher for platinum nanorods compared to the planar platinum. And this is at small diameters, and as we go to large diameters, this effect fades away. So in the remainder of the talk, I'll show some intraoperative results done with both P dot and platinum nanorods. This work is done at Mass General Hospital in collaboration with the group of Sydney Cash. And we see a bipolar electrode that's being used for disruption of function, for electrical stimulation disruption of function. Our electrodes are placed right here. There is video tracking of the location of the stimulating electrode with respect to the microelectrodes so that we can correlate the effect of distance stimulation while we are recording potentials on the microelectrodes. Here we're using a small pitch arrays with 50 micron side-to-side spacing in two columns, 128 in total. And so this is relatively where the simulation is with respect to the recording array. And we can see from the cumulative plot from all channels that at about 1.5 seconds into the recording, we see eruption of waves of local field potentials. If we plot that spatially on the two grids, we see that the wave propagates closer to the stimulation site up to the top of the array. There is changes not only in the temporal signature of these waves, but also in their amplitude on distances of about 100 to 200 microns. This is used also in some of the epilepsy cases where the arrays are placed in between or next to clinical electrodes. So we see that when we record the interictal epilepsy discharges on the clinical electrodes, which are shown over here, we can also record them on the research electrodes. These are 128 channels, 4 banks of 32 channels. Now here the activity is a little bit faster, so it's a little bit harder to see the propagation of wave. But what we can see from the color coding is that at one side of the electrode array, we have larger potentials. As the wave propagates to the other side, we have smaller potentials, and there is a little bit of delay in the maximum peak of these waves. Now, in some of the language tasks, first, the localization of different brain regions is done with a conventional epilepsy grid. And then once we know, or once the neurosurgeons know exactly where's the superior temporal gyrus, for example, which processes language versus other brain regions, we place our microelectrode arrays just over that region. And what we're looking at here is the high gamma activity from about 60 trials. On the y-axis, we have the distance across the array, the 2-column array. This is as a function of time. And the responses here are being measured when the patient is listening to auditory stimuli. In some cases, they don't make any sense, or for proper words, or just noise. And we can see that when there are letters that don't make sense or complete words, we have sharp responses where noise does not provide any response. And similarly, the regions that did not respond to the words have some response in the noise and a little bit of response also in the words and nonsense. So we have basically oppositely responding regions for words, nonsense, compared to noise. But what's remarkable here is that the transitions from the responsive regions to the non-responsive regions are relatively sharp, on the order of a few hundreds of microns. If we take a look here through line cuts, through the averages of all of these trials, we can see that some of these transitions extend from 450 microns to about 250 microns. And this work is done in collaboration with Eric Hallgren here at UCSD. Now we move to recordings with the 1024 arrays. These could be configured in tight pitch or in large coverage. We'll first start with the tight pitch. This is a 16 by 64 array. And the video right here shows the placement at OHSU of these arrays on the cortical surface of a patient undergoing a tumor resection. Now the electrode is transparent. So you could see the anatomy of the brain while you are placing it, but it's also hard to handle because it's very thin. And you can kind of see the electrode only when it reflects light from the surface. Now this is Dan Cleary, a neurosurgery resident postdoc in my lab, who is conducting the awake discussion with the patient. Now, the electrode was placed in this case over the Broca's area. And similar to the case of the 128 channel arrays, we're looking at responses for nonsense auditory stimuli, stimuli with words or with noise. And we can see here as well that regions that are responsive to the auditory stimuli are non-responsive in the noise stimuli. There are additionally fragments or stripes of responsive regions in addition to a few individual units that are responsive right here. So this is giving us an early glimpse of the functional organization of language processing in the human brain. Now, about 2 weeks ago, we had our first case in which we've done motor mapping, where the patient is being instructed to
the middle finger together.
Move specific fingers
you're doing a great
where we are
job.
tracking the movement.
Keep
And
going.
time locking this movement to the recorded activity from the surface of the brain.
For a few seconds.
Right, so I'm gonna show you in a second where basically how the activity looks like, but this is the placement of the electrode on the patient's brain, and there are still non-idealities. We can see that there are regions which have CSF bubbles underneath, so that prevent us from recording uniformly across the whole array, and these are things that we can overcome by creating perfusion holes to let the CSF come out through the electrode. Now I'm going to show you a video about the type of activity that we see here for trial averages of 57 cycles of flexion and extension. And what we're going to see is basically a wave that propagates from the top left to the bottom right. And we're going to also see that the activity that you see right here is roughly showing a dipole or a source sink configuration with a nearby region. So let's see, and you can see first the negative portion of the wave propagates, and then we'll see that the yellow higher potential also comes across the same path. And then in a second you will see once more that the high potentials appear when the potential is low on this side, and so on. This is a relatively new process, just yesterday, and we're very excited about this result. Again, looking at the trial averages for the flexion of the finger and then the recorded signal, we see consistent responses across all trials. What perhaps you have noticed in the video is that the movement of the finger was happening periodically after each other, so the times for each trial are varying between one trial and the other, which basically complicates a little bit time locking of the phases between the two signals. Right, so I'd like to finish up by saying that we just started using these electrodes in assisting neurosurgery in the spinal cord, where one needs to do neuromonitoring during removal of tumors in the spinal cord, for example. So we have peripheral nerve stimulation recording the spinal cord, or cortical stimulation and recording in the spinal cord, transmission of the signals in the spinal cord. The stimulation here is done at a frequency of about 2.8 hertz in order to delineate the responses from any of the signals that are in the environment. And we see from the recordings that that's, after a little bit of time delay, that's what we record from the spinal cord. What the significance of these results is that with clinical stimulation, typically one needs about 16 milliamps or so to induce activity and record it with the strip electrodes, but with the thin flexible electrodes, we can do that with about 2 milliamps. And the same is true for the cortical stimulation. Now, this is a large collaboration effort, and I'm very lucky to have excellent collaborators with whom I interact and supervise a number of students and postdocs, particularly Eric Hallegren and Sid Cash at MGH and Ahmed Reslan at OHSU. The team that has contributed to the 1024 arrays is mainly Andrew Bourhis and Yongbin Chui. Jiwan is taking these advances and doing penetrating laminars for human use. On the spinal cord side, Joe Sayasi and Sharona Binhayim are the leads on the medical side. So the work is mainly supported by the NSF. We just received support from the NIH, and over the last 5 or 6 years, we've had several grants from the Center for Brain Activity Mapping here at UCSD that allowed me to develop these ideas together with my collaborators. So thanks for your attention. I'd be happy to take any questions.
Actually, it was great. So going all the way from electrode materials to neuroscience and clinical applications. Some questions?
Thanks for the talk. There we go. So I was curious about the geometry, the width and the thickness of the traces on your 1K array, and what was the cable impedance over 10 centimeter length?
Right, so the width of the lead is about 5 microns. Right now we're working with. Pitch is 10 microns. Impedance is, well, the resistance is about 3 to 10 kilo ohms, depending on how far in the contacts. Usually the contact impedance is about 20 kilo ohms for 30 microns. So we're just lower than the contact impedance itself. Thank you.
So I have a question. So this is amazing, I guess, technologies here, right? So I noticed on your electrode impedances that you get usual, I guess, dependence on area, right? But for the nanorods, it seems that for the larger areas, you didn't quite get the same advantages than for that you got for small areas. Could you explain why that happens?
Yeah, so usually the impedance actually at micro scale is dictated by the circumference, where edge effects are usually maximal. And as we go to larger contacts, these edge effects have lower of an influence. So we see the maximum benefits in platinum nanorods at smaller contacts where this edge effect is really large, and it decays as we go to larger contacts. And the reason over there is mainly current crowding at the edge of the contact that contributes to a series resistance which scales with circumference. And this effect fades away as we go to larger contacts.
So that suggests you may be better off having islands of electrodes rather than solid electrodes, right?
Yes, we're exploring that for larger current carrying electrodes.
Some more questions? Bruce.
Well, I'm just curious. You get all of these great surface recordings, but people who are recording from the surfaces of EEGs often think about source localization. Do you think at all about that? How can you detect depth of signal underneath your array? Can you focus up and down, so to speak?
This is a golden question if we're able to answer it, and we're trying to do that both in animals and in humans. In animals, what we're trying to do is work with colleagues who do 2-photon imaging, like Anna DeVore, in which we can look at the calcium signal during the activity and correlate this calcium signal with the electrophysiology that we record from the surface of the brain to know exactly, where is the source of these signals. In humans, when there is tumor resection, we're looking at stimulation subcortically and recording cortically to be able to map the eruption of activity due to stimulation.
Some more questions? Well, with that, let's thank Shadi again.
Thank you.